Hello everyone, welcome to chapter 3 on derivatives. We look at tangents and derivatives at a point. This will be more of a recap of what we saw in the introductory chapter where we spoke about secant line and tangent line. So let's do a quick recap of that. So say this was the curve and you had a line passing through this curve that touched 2 points on the curve, say P and Q. If P was let's say a particular point, x0, f of x0. Then Q was h units away on the x-axis with x0 plus h, f of x0 plus h. All right. Now, we saw that the definition here was that when a line passes through 2 points on a curve, it is equal to a secant line. I'm going to write that now. So the definition is written there for us. Now, we said that if we wanted to talk about moving that point Q closer and closer to P, so that at one situation, at one instance, you do not have a P and a Q separately because Q has coincided with P. Now, if that was the case, then you will now have a tangent line at P. And so it's basically just that one point through which the line passes, and that point is a point that's on the curve and on the line. So a line that passes through only one point on a curve is the tangent line. So now if I combine these two, the PQ and the the two scenarios here, you can see that P and Q, x0 f of x0, Q is x0 plus h, f of x0 plus h. And what we said was this black line that connects P and Q, which is called as the secant line, becomes this pink line, which is the tangent line, if this h value, right, this distance between the 2 points becomes 0. And that was the idea of limits. And so we're going to combine these two to write our formula here. Okay. Now let's understand that we'll start off with what we know. So the slope of the line, the secant line, I'll say, PQ, we know the slope, M secant is f of x0 plus h minus f of x0, y2 minus y1, over x2 minus x1. x2 here is x0 plus h minus x0. And we can clearly see that these will go away. And so this formula reduces to f of x0 plus h minus f of x0 all over h, basically the distance between the 2 points. Yeah. Now, this is where we are interested in finding the slope of the tangent line, or in other words, the slope of the curve at the point P. I hope you can follow along the crucial difference in the language here. When I say slope of this pink line, you can see that slope of a line is meaningful. But instead, if I said slope of the curve, that means I'm looking at the blue curve now, slope of the curve at the point P. And we know that we can answer that question, slope of the curve. Now, we've never heard that, right? Its slope is always related to a line, not a curve. But here we're saying slope of the curve at a point P makes it possible for us to consider what that point shares. The point shares the same location as the tangent line, right? Because the tangent line and the curve have one common point, which is the point P. Therefore, we will say the slope of the curve at P will be the same as the slope of the tangent line at P, because it's tangent, it's touching. And the only way this can be done, because even if it's a tangent line and we want to find the slope of this pink line, we still need 2 points. And what we did was we said, well, the other point is coinciding with P. In other words, we're allowing Q to approach P. Okay. This implies we allow the point Q to approach P. And so if Q should approach P, that means H must be 0. So we must allow H to approach 0. And we know that the notation for that is H approaches 0, right? Now we are able to define slope of the curve at P using the limit notation. It will be the same as slope of the tangent line. Notice how there it was m secant, right? M with the suffix secant, and here it's m with the suffix tangent. So m tangent will be limit as h approaches 0, right? F of x naught plus h minus f of x naught all over h. So we're taking the secant, the slope of the secant line, and there we allow h to approach 0 using the idea of limits, and that will help us to locate this. And of course, provided the limit exists, right? If it doesn't exist, we've seen examples of how that can be also the case. So we have to indicate that if the limit exists, then we can find the slope of the curve at that point P. All right. Also, in pre-calculus, you would have learned about this expression, this part here. This expression was seen as the difference quotient. So let me write that out here. Okay. So you're taking the limit of the difference quotient. So that will be f of x naught plus h minus f of x naught all over h. And for this difference quotient, when we apply the limits, it will now be called by a new name and a new notation. And so once I apply the limit, then we talk about the rate of change, or it's also known as the derivative at a point. So let me write that information here, okay? So when we apply limits to difference quotient, it takes a new name and a new notation. So what it will appear now will be f of f with a stroke there, we call it the prime, f prime of x naught, right? And that stroke is really important because it means, because that's the notation here and it means something else, right? So f prime of x naught is limit as h approaches 0 and then the difference quotient, which is this. We just saw that. Looks like we're repeating this over and over, but we're trying to make overall connections, because this was the same as m tan, right? Slope of the tangent line. But what we see here is that this notation affords a new understanding, where this is called as the rate of change at a point. Remember again, rate of change was usually from one point to another, but here we're talking about rate of change at a point. But that is actually upgraded. This language is again upgraded to this new term. We call it the derivative at a point. Okay, because we derived the slope at a point instead of between 2 points, and so we call it the derivative. So derivative is the name for it. The notation is f prime of x naught, and the expression is the limit of the dq, difference quotient, as h approaches 0. So what does this do? What does the limit of dq mean? It means several things, as we saw. It means the slope of a curve at a point. It means the slope of the tangent line at a point. It also means the rate of change, as we saw here, at a point. It also means derivative. So it takes on 4 meanings depending on the type of problem that we're trying to address. If it's word problem, you'll usually see the language rate of change, perhaps, right? If we are talking about in a graphical sense, then we could be looking at the tangent line to the curve at that point. And when we say derivative, that could be a very calculus-oriented problem. So it takes on different meanings because it's not limited to just math. The application is in every field imaginable. First off, I have provided a proper definition, a formal definition. So let me read that so we can have that language kind of ingrained there for us. We're going to use this a lot. The derivative of a function f at a point x naught is denoted by f prime of x naught, and it is the limit of the difference quotient, provided this limit exists. So I want you to again pay attention to the language here. The derivative of a function, you derived it for the function, but at a point x naught. So you see here, it is not f prime of x, it's f prime of x naught, because that means you're finding the derivative of the function at a point x naught. So this is the expansion for this notation, f prime of x naught. That notation expands in words as seen in as written in bold there. Okay, so that's a formal definition, and I was talking about how we can interpret this. So let's check this out. The following are all interpretations for the limit of the difference quotient. So it can be seen as the slope of the graph at x equals x naught, which means in this case it will be the curve, right? The graph was the curve. If it was a line, we have no problem because we can find the slope of a line directly. We don't have any difficulty in explaining that. The whole challenge of this calculus problem here is that how do I find the slope of a curve? We have a way to find the slope of a line. And to find the slope of a curve, we use the idea of limits. And therefore the slope of the graph is basically a curve. And because the curve and the tangent line meet at a point, it can also be seen as the slope of the tangent line to the curve. And in real world situations, we call it as the rate of change of f of x with respect to x at that point x equals x naught. And lastly, we learned about this new term, derivative f prime at a point. Okay, and the point was x naught. So we have these things. It's better understood through problems, so let's get started on that. Let's read this problem. Find the slope of a function at the given point. Then find the equation for the tangent line at the point. And then the function is given to be f of x equals x squared plus 1, and the point specified to be 2, 5. We get the idea that we want to find the slope of this function. So x squared plus 1, you can kind of visualize this because it's a simple function, or you could use your calculator to graph this function. Now, you know x squared is going to be a graph, a parabola that opens upwards. Plus 1 would be one unit up. And so using transformations, you can see that your graph will be like this. And if it's 2, 5, it's probably some point here, 2, 5. And they want us to find the slope of the tangent line and then the equation for that tangent line. So this is the gist, the idea of what we have at hand. And so we can understand that we're supposed to find m tan, right? Slope of the tangent line. Because they've asked us to find the slope of the function, but you know slope of the function, or in this case the curve, which is also known as the function, because they've given that y equals f of x. So the slope of the function at a given point, that's what they're asking us to find, which is the same as finding the derivative, right? So you can write it as f prime of the point, and the point for us is given to be the 2, right? So in order to, this is causing a little confusion because we're not sure whether it's a 2 or the 5. It should be the 2 because it's all about x naught. This is your x naught, right? And this will be your f of x naught. So this will be your f prime of 2. Okay. But for the moment, let's skip that notation. We'll come in the end and then we can worry about that, because ultimately the question was to find the slope and then to find the equation. So don't worry about giving it as a derivative, because the derivative notation could be utilized when they specify for the derivative. Right now, because it's a slope, I'm sticking to the m tan notation, and that is defined to be limit as h approaches 0, f of x naught plus h minus f of x naught all over h. Okay, so I have, the x naught, and then I need the h. So we have actually only one point given to us, right? So let's, because we're familiar with p and q, so you can think of p as 2, 5. We need another point q so that you can then allow the Q to approach P. So we know that the point Q is h units away from the point P. So it is 2 plus h and correspondingly f of 2 plus h. That's how you can define the other point. So I'll just say here, since we have only one point given, we make another point using h, because you know that is kind of your help there. And then we allow h to approach 0. So that's our plan, and we generated the Q point. So now it will be easy for us to do the f of x naught plus h and this one. So let me come over here. So we already said this is going to be x naught and f of x naught. And this will be x naught plus h, and that's what we have, right? 2 plus h, comma, f of x naught plus h. So this will now help us to plug them in appropriately. Okay. So m tan is limit h approaches 0. F of x naught plus h is the same as f of 2 plus h minus f of x naught is 5 divided by x naught plus h is 2 plus h minus x naught is 2. And as expected, the 2's will cancel off, leaving us with just an h. But if you come to the numerator, f of 2 plus h, how do I evaluate that? For that, we have to go back to the function. This is f of x, right? F of x is x squared plus 1. So if f of x is x squared plus 1, it implies that f of 2 plus h will replace the x, right? So in the place of x, I'll now have 2 plus h. And please be very careful on the substitution part, because sometimes this is what I've seen students do. When they do f of 2 plus h, what they mistakenly do is they write this x squared plus 1 and simply add the h. That is not right. You're not adding an h. If you're adding an h, the expression will be f of x plus h outside the x. But this is not the same as f of x plus h, where the whole function is evaluated at x plus h. So please note this crucial difference, and that these are the things that you learned in algebra. So I want you to recall those concepts there. And so do not mistakenly do this, because this will not lead us to the answer. Okay? And so so I'm going to remove this part. No, I'll leave it there just as a reminder for us. Okay, so I'll come back to m tan, and this time I'm going to substitute for f of 2 plus h as 2 plus h the whole squared plus 1 minus 5 all over h. Now 2 plus h the whole squared, again algebra, where you either multiply it twice and FOIL it, or you remember the a plus b the whole squared formula, which is, let me write it by the side here, a plus b the whole squared. You can either write it like this, a plus b times a plus b and FOIL it, or the formula is a squared plus 2ab plus b squared. Okay, so use one of these, and this is what you should get. Keep the limit h approaches 0 tagged along in every step. We don't want to miss out on that. So that's going to be 4 plus 4h plus h squared plus 1 minus 5 will be a minus 4 all over h. Okay. The 4 and the minus 4 will cancel off. You'll actually begin to see that by default, all non-h terms, like the 4 and the minus 4, right? They didn't have any h in them. All the non-h terms in the numerator must cancel off. That's by default, by the way it is set up. So if you mistakenly did something like this, where you added the h in the end and did some messy things like that, you will not get that situation happening. You will not be able to eliminate the non-h terms. So that's another way to kind of make sure that you didn't go off track. Okay, so all those things will cancel off, leaving us with terms that contain h only. That allows us to factor out an h. So you have h that's common, so you can factor out an h. That will make it 4 plus h on the top all over h. Now this is super important because we want the denominator to go away. Because if the denominator stays and you have to plug in for the limit of h as 0, you'll get an undefined situation, right? And so this technique assures that you will have an h that will cancel, that can be pulled out on the top and can be cancelled with the h in the bottom. And this is wonderful because now you have a setup where limit h approaches 0, 4 plus h, allows you to substitute for h as 0. So you get 4 plus 0, which is 4, which is giving you a lovely answer, right? Meaning your slope of the tangent line is 4. So without the h cancelling off, we wouldn't be able to substitute for h. So then I'll come down here and say m tan, the slope of the tangent line is 4. So we answered the first part of the question. They said find the slope of the function at the given point 2, 5. So we answered that part. Now we need to find the equation for the tangent line at that point. Remember, equation of a line, it's a tangent line, so it's a line. So equation of a line, we have several forms, right? The slope-intercept form, the standard form, and the slope point form. At this juncture, you realize that you just found the slope and you have the point. So of the three options we have, the slope point form is the most useful version. And what does this form say? This says y minus y1 equals m times x minus x1. And so I'm going to plug in for y1, which is the 5 in our point, right? That's your y coordinate, equals m, we found that to be 4. You only plug in for x1 and y1, not the x and the y. You need your equation in x and y. And then your your x1 will be the 2 that we got from there. So these are the pink ones are the places where you substituted. And so you have y minus 5 equals 4x minus 8. Distribute. Okay. And then y equals 4x. Add the 5 on both sides and it gives you minus 3. And we found the equation of the tangent line at the point 2, 5. TGT for tangent line, okay, just short for that. And that's it. You got your answer right there. And we always want to understand what the question asks for. And like in this case, we had 2 parts, and make sure you answer both the parts. First of all, by sequence, you will need both the parts, right? You will need the slope in order to even write the equation, but always try to highlight these answers. Next question would be, find the slope of the curve y equals x minus 1, I'll write that clearly, x minus 1 over x plus 1, x equals 0. Okay. So here they didn't ask for the equation, they asked just for the slope. So remember, we need to find 2 points, right? We need the p. So the point that's usually given to us will be the p. So first of all, the p, in the p, the point, we were not given the full set of the coordinates. We were just given the x coordinate. Okay. So to find p, point p, we need to understand that we need to find the y coordinate. So plug in for 0. Okay. That gives us -1. So the point P is 0, -1. Okay. Is one of the points. So in order to generate the Q, you know that we will have to add an h to this. So 0 plus h. Again, don't add an h to the -1 because that will be false. 0 plus h, we don't know what h is, so you'll have to only do f of 0 plus h. Well, 0 plus h is the same as h itself. So I'll just simply rewrite this as h plus f of h. Okay. Now, just a quick help here. F of h will be wherever your x occurs, you can now plug in h. So h minus 1 over h plus 1 from our given equation. So we got all the things we need set up for us. Now let's go ahead and find the slope. So m tan is limit h approaches 0, f of x naught plus h minus f of x naught over h. And so quick reminder, this was our x naught because that's our p, right? F of x naught. And this is our x naught plus h and f of x naught plus h. F of x naught plus h is f of h minus f of x naught is a minus 1. Notice there's double minus there. There's a minus in the formula, and f of x naught itself is another minus 1. So we have that. And then we have x naught plus h minus 0. Okay. You can look at the p and the q and do y2 minus y1 over x2 minus x1. F of h is h minus 1 over h plus 1. And minus of minus, combine these two, right? If you combine those two, that becomes a plus. So you have a plus 1 all over h. What we have before us is a complex fraction, which means a fraction within a fraction. And if you look at the numerator, there is a fraction within it. And so we have to first address that using LCD. The denominator, no problem. For the numerator, the LCD would be that you want to have them with the same denominator. So multiply up and down by h plus 1. And that gives us h minus 1. So h plus 1 is common, right? So combine the numerators. So h minus 1 plus h plus 1 and all that over h. And as expected, we would have the non-h terms to cancel away. Okay. So we have so that's the numerator is 2h over h plus 1, right? The numerator is 2h over h plus 1 times the flip of the denominator. That's how you handle two fractions. So I put a 1 underneath the h in the denominator so we can see the flip of it. So the numerator times the reciprocal of the denominator. So h over 1 becomes 1 over h. Okay. And that, as we expected, the h will be available to cancel off with the h in the bottom. Well, you see that there is still an h left in the bottom. Usually they all go away. This is a case where it doesn't go away, but it's in a totally good situation because you are going to plug in for h as 0, but that doesn't make your denominator 0 because of that plus 1. So I'm going to take it one more step so you can see clearly what we're left with. 2 over h plus 1, and when you plug in for h as 0, you get 2 over 0 plus 1, which is 2 over 1, which turns out to be 2. So we got a very nice number here. We didn't have an undefined situation because of that plus 1 that saved us. Okay. And we always get that set up. So even if you have an h left in the bottom, it won't be an h by itself. It'll be combined with some other terms so that when h takes the value 0, you'll still be left with some other numbers, and that will help us. So the question was to find the slope of the curve. So the slope of the curve at x equals 0 is 2. And if you wanted to go further and if you wanted to find the equation of a line, I'll just give you that help as well. Equation of the tangent line. This is the slope, right? So I'll do y minus y1, which is negative 1, equals slope, which is 2 times x minus x1, which was 0. Because the point was 0, x1, right? 0, negative 1. 0, negative 1. So I plug in negative 1 for y and 0 for the x. So that will be y plus 1 equals 2x, and then y equals 2x minus 1. So if the question asked you to go further and find the equation of the tangent line, we got that as well. Now, if they say find the average rate of change of the function f of x, from x equals -2 to x equals 5. And the function is given to be f of x equals x squared plus 3x minus 1. And if you're asked to find that, then it's pretty much straightforward, right? You see that you can get your, when x is equal to -2, it implies f of -2, because you're given 2 points. You're asked to find the average rate of change. Remember, rate of change is another name for finding the slope. But here, here they gave us the 2 separate points. We didn't have to generate the second point. So all we have to do is find the corresponding y coordinates for these. So -2 the whole squared plus 3 times -2 minus 1. Okay. And that comes out to be -3. When x is equal to 5, f of 5 would be 5 squared plus 3 times 5 minus 1, which comes out to be 39. So I would have my coordinates, okay, slope between -2, -3 and 5, 39, right? This would be the slope of the secant line because it's between 2 points. So it implies you're not finding m tan, you're basically finding m secant. So m secant is y2 minus y1. So there is no limit here. Okay, let's remember that. There is no limit here because we're not talking about the tangent line, we're talking about the secant line because it's between 2 numerical points. We didn't generate the second point. 39 minus -3 over 5 minus -2. So that will be 42 over 7, which is 6. So the average rate of change between these 2 points was 6. Okay. And let's take a look at the next problem, which is going to look similar, but we'll take a different approach. For the function f of x equals -x squared minus 3x minus 1, compute the average rate of change over successively smaller intervals to estimate the instantaneous rate change at x equals 1. Now look at the question. It's sounding tricky here because it's like it says average rate of change, but then they have this extra language that says successively small intervals and the instantaneous rate of change at x equals 1. So what is it that they're really asking us? Okay, let's look at this one. Okay, this actually helps us to see if we understood the concept in general. Okay, so think of, now you know this is a parabola, right? X squared, the degree 2 is a parabola. Because of the minus, you know it's going to open downwards. So let's think of this like this, right? This is going to be a parabola that opens downwards. And so we're trying to look at this near x equals 1. Okay, so probably, let me draw this like this. I'm not sure. Say, let's say, when x equals 1 is here. Okay, that's the point when x equals 1. And we can see that that will be the slope of the tangent line at 1. Okay? And we can evaluate for 1 by plugging in the function at 1. So we can find that. And what we are seeing now is that we need to find successively smaller intervals to estimate what happens at 1. So we're going to look in the neighborhood of 1. Okay. So because this is a continuous function, and because of the continuity, we can approach from the right or from the left, right? And they will point to the same limit value. Therefore, we can look at, we can choose to look at to the right of 1. And so I'll have these intervals. Okay, what happens between 1 to 2? then I have to make it smaller, right? Because it's a successively smaller interval. So I'm only looking at the right of 1, because we know that it's continuous function, it's a polynomial. So both sides will point to the same limit value, the same L. So just focus on the right side. And then I go for 1, 1.5. I've reduced the interval, okay? From 1 to 2, I've reduced the interval to 1 to 1.5. Then again, reduce it, okay? Make it even smaller. What will be the slope if I took the interval from 1 to 1.1? Okay. Make it even smaller. 1 to 1.01, and let's see what happens for the slope for each one of them. So you're basically going to compute it for each one of them. Okay. So m secant f of 2 minus f of 1 over 2 minus 1. Okay. You're going to plug in for f of 2. So in your function, in the place of, in your f of x function, in the place of x, you're going to plug in 2 everywhere. Okay. Negative 2 squared minus 3 times 2 minus 1. That is for the 2. Minus f of 1. Now plug in for x as 1. All over 2 minus 1, which is 1. So you're going to compute this, and what we get on the top for this one is negative 11 minus negative 5 all over 1. So it's going to be negative 11 plus 5 over 1, which is negative 6. So when you took the interval 1 to 2, you got a negative 6. So I'm going to allow you to pause the video and compute it on your own for each one of them, and then you can come back to see what the answer would be. So f of 1.5 minus f of 1 over 1.5 minus 1. That will be for the next smaller interval, and that gives us negative 7.75 minus negative 5 all over 0.5. That comes out to be negative 5.5. Notice that when my interval was reduced, the slope also changed. From a negative 6, it became a negative 5.5. For the next successive interval, which was 1.1, right, 1 to 1.1, so 1.1 minus f of 1 over 1.1 minus 1. You can see that it's steadily reducing. And let's check out for the last interval. And that gives us negative 5.01. Okay. So in fact, we should have started at 1.01 because you want it to get really, really close. You want the 2 points to coincide. You want the second point to come closer and closer to the first point. And so our focus is on 1. So you want to keep the interval closer and closer and closer. So what we see is that if I kept my interval, so I'm just going to zoom in between 1 and 2, right? So we had 1 and 2, then we reduced it to 1.5, then we said 1.1, and then we went to 1.01. But what I'm saying is let's zoom in between 1 and 1.01. So then you can actually bring in all these points, 1.0001, 1.001, 1 point, okay, you got that. So if you were doing that, just increasing the number of zeros, that would actually bring you closer and closer to negative 5, because you'll get negative 5.00 something, and then you get closer and closer to the 1, and then you realize that your average rate of change appears to be approaching negative 5. All right. So this is the idea of limits. They just this question just asks you to do it manually to explain that process. So we say that the average rate of change over these successively smaller intervals appears to be approaching -5. But if we did the same problem, okay, so that's what we're going to do now. If we take the same problem and used another point Q, so we got x equals 1, right? This was near x equals 1, so we got f of 1, I should say, to be -1 squared. We did that, so I'm just going to show that to you here. -1 squared minus 3 times 1 minus 1. We got that to be -5. Okay. And then we can use that as our point P, which is 1, -5. And Q will be 1 plus H, f of 1 plus H. This is the case where instead of developing those smaller intervals, you are actually creating another point Q by moving it a distance H units away from the P. And then we could use, instead of M secant, but for that problem, they wanted us to find the average rate of change. So we were able to use the secant to make the change. But here we can support this answer, or cross-check this answer through M tan, which is supposed to kind of give us an answer that is -5, because that was our hunch when we chose those small intervals. -1. So I've plugged in for f of x0 plus h, okay, minus f of x0 was 1. No, -5. F of x0 is -5 all over h. Again, to the a plus b the whole squared formula. -3 distribute the -3 all over h. Now combine all like terms. So when I combine all the numbers, -1 and -3, I get -4. -2h and -3h is -5h minus h squared. And -1 plus 5 is +4 over h. And you know that we always have to verify if the non-h terms go away, and it does. That's good. And then we can actually pull out a -h from the numerator. That leaves us with 5 plus h. Remember, you pull out a negative, so it has to be 5 plus h all over h. And then the h's cancel off as expected again. So we have limit h approaches 0, -5 minus h. It seems like we didn't have to pull out the negative, but that's fine. I distributed the minus back inside. And now when we substitute for h as 0, I have -5 minus 0, which is -5. And this is what we got from understanding the instantaneous rate of change at x equals 1 by bringing the intervals closer. The same idea is applied here by allowing h to approach 0. This question says, find g prime of -9. Notice how the notation is used to indicate the derivative from g of x equals -2x plus 8 all over 3x minus 9 using the definition of derivatives. We learnt about this new term here, right? The new term was that f prime of x naught, which is the same as the slope of the tangent line, is called as the derivative. The derivative is the slope of the tangent line. And the notation for that is f prime of x naught. Here in this problem, instead of using f, they use the function g. It doesn't change anything. So we will just go back and define this. The definition of the derivative is, so I'm going to write the definition using g. So instead of f prime, I now have g prime. G prime of x naught is limit h approaches 0, g of x naught plus h minus g of x naught all over h. Right? So what we had for f, we converted for g to make a quick connection here. And so if we were to find g prime of -9, your x naught is -9. So in your formula or in your definition, you're going to plug in -9 for x naught all over h. Okay. So now let's define our p, right? The point p. We know that it's -9. Let me just write here. If x is -9, this implies g of -9. We need to find g prime, but we can find g of -9 by plugging it back in this g function, -2x plus 8 over 3x minus 9. -2x plus 8 over 3x minus 9, and I left a parentheses to plug in for -9 in the place of x. Because there's a negative, we want to be super careful. I can't insist enough on this, because right there you can see double negative in play. And so that's going to be positive 18 plus 8 over -27 minus 9, which is 26 over -36, which can be negative, which reduces to -13 over 18. Okay, so your p, point p, is -9, -13 over 18. And then we'll generate the q. Q is -9 plus h, and f, oh, not f here, it's g. G of -9 plus h. And so we say g prime of -9 is limit h approaches 0, g of -9 plus h minus -13 over 8 divided by -9 plus h minus a -9. Look at the double negative there. G of -9 plus h will be actually -2 times -9 plus h over, no, it was -2x. I'm plugging in the function, okay? -2x plus 8 over 3 times x minus 9. So 3 times -9 plus h minus 9. Put this like this. That's your g of -9 plus h. plus 13 over 18, because you combine these two, all over negative 9 plus h plus a 9, and therefore these will go away. Okay, we do have a complex fraction now. We have to watch carefully because it's a bigger expression than before. Okay, distribute on the top. So we're focusing only on what is happening. So I'll just put the same color here so we can focus on what's happening there. So that will be 18 minus 2h plus 8 over negative 27 plus 3h minus 9. Okay, that plus 13 over 18 all over h. It'll be so much easier if we just, can see that it's basically 1 over h, this h, times this whole thing. Right? So anyway, if you can't see that yet, that's fine. We'll come back here and this expression, 18 plus 8, (26) minus 2h over negative 27, negative 36 plus 3h plus 13 over 18 all over h. Okay, for convenience, I'm just going to cross multiply. I'm not taking the LCD necessarily here. The cross multiplying gives you the same effect. It's just that you have smaller terms to deal with if it is LCD. But remember, we are in calculus, so we should feel free to utilize techniques that are helpful. All right, now at this time you could pause the video and start calculating on your own, and we can compare our answers here. When I computed this, I got this expression, and right there I feel very confident because 468 and negative 468 will cancel off, and I can see that I can pull out an h there, right? And then we can come back to checking out the denominator. Well, now remember to flip the denominator. This is h over 1, and we will flip that. The h's go away as expected. After cancelling out the h's, we have 3 over negative 648 plus 54h. And so I can pull out a 54 in the bottom. That gives me negative 12 plus h. Okay. And we know that the 3 and the 54, they cancel each other 18 times. (1 over 18 times negative 12 plus h). And now we can plug in for h as 0. Which is 1 over 18 times negative 12, which is 1 over negative 216. But we write usually the negative on the top so that it's visible. Nothing wrong. So this or this is fine, but we usually like to put the negative on the top. And that is our answer. G prime, or the derivative of g at negative 9 is negative 1 over 216. So I know this problem looked intimidating, but don't give up because these are just algebra here. And we're in calculus, so we're supposed to handle sometimes these kind of problems. And this also tells us how to be strong in our algebraic skills. All right, class. So we've come to the end of this section in this series on Chapter 3. And I will see you in the next video continuing with Chapter 3. See ya.